All right. Today we will finish up some circuits and address many of the homework questions. A lot of you have probably been looking at going, I don't know, because we haven't addressed in lecture, just only the textbook you've had to help you. So get to those. We'll review Ohm's Law, talk about AC and DC circuits, electric power, because that's how they charge us from the power company, and series and parallel circuits, because we use those all over the place. That's my goal for today. To start, I have a few questions for you. So, review, see what we picked up from up till now, so you can dig your clickers out. I'm going to start with this one. I know you're still digging them out, but polling's open. 3 different statements there. Which one's correct, or all of them? What do you think? I'm well aware we get lots of terms in physics class that, you know, there's, in a sense, there's kind of a lot of new definitions. You're like, oh, temperature, heat, current, voltage, potential. Oh, we got over half of you. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Did you get it out in time? 0. 61% think it's B. You are correct. You are correct. Voltage does what in a circuit? What do you think of when you think of voltage in a circuit?
Pushes the charge through.
It's what pushes the charge through, yeah. Charge won't flow unless there's a difference in voltage, difference in potential. You have a voltage. If this is at 9 volts and this is at 9 volts, nothing's going to flow between. But if you have this at 200 volts and this at 100 volts, now there's an electric field. The charges feel it and they get moved along. What was C? A battery is the source of electrons in a circuit? No. What is the source of electrons? The circuit itself. Very good. You read. The charges are already there. The electric field, once it gets established, just allows them to start moving. Because remember, if you set up an electric field and you put a charge in that electric field, it's going to get accelerated, feel a force. Positives will go towards the negative side, and negatives will go the other way. Because opposites attract and like charges repel. All right, not that one. This one. Go. You double the voltage in a circuit, what else doubles? So you have a certain circuit, say it's like 120 volts. And then all of a sudden you put 240 volts on it. Same circuit, what happens? You double the voltage. This is Ohm's Law, that relationship. I'll even write it down. Something's wrong with the board. Rearrange it. Same equation written 3 ways. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, we're kind of split. 45% think it's A, but about 25-30% think the others. I'm just going to give it to you. And this time it is A, current. Voltage is what pushes the charges through. If you have a certain circuit, the resistance of that circuit is going to determine how much charge goes through as well. Ohm's law is that ratio. How much charge flows depends on how big a push it has and how much resistance there is. If you're not changing the circuit, you're not changing the resistance. But if you double the voltage, you get twice the push. You can push twice as much current through. Does that make sense? And I think there was one more I wanted to do. It is that one. All right? Let's see if you can use Ohm's law now with some numbers. And your equation for your guide to thinking and solving is on the board. If you're actually given a voltage and a resistance, can you determine how much current's flowing? Charge is flowing, how much current there is. So this gives us the push, the voltage, how much energy per charge is going to all those charges to make them move. But then how much resistance is in the circuit and is going to try to impede those charges. Both of those determine how much current. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. 88% say A. Good, you're solving it correctly. 110 volts over 22 ohms. I failed to mention that resistance is measured in ohms, another guy's last name. And you solve that, you get 5 volts per ohm is current. And current is measured in amps, amperes. French guy. Any questions? All right, you can put your clickers away then. I want to emphasize briefly with resistance. I touched on it with the water flow. Reiterate, revisit. If you have water flowing through pipes, which one do you think will provide more resistance to that water flow? You're right, this one. How about with charge? Now you're not as sure. You can think of charges as flowing. And there's an electric field, a difference in potential, trying to push it through, just like you might have difference in pressure, trying to push water through. And if you have something that's narrower, a conductor that's narrower, so that the charge is free to move on a conductor, so a skinny wire versus a fat wire, this is harder to get through as well. So this has more resistance. And you can use that analogy of the water. You're trying to cram it through a smaller opening, it will get harder. Current is the flow rate of charge. And if you're pushing the same in each of these, it'll have to it'll slow down as you confine it. Eventually the same charge can get through, but it won't go as fast. All right. What if you had this wire and that wire? Which one has more resistance? I'm hearing more of the bottom, the longer one, than I am the other. That's correct. If you got more stuff to go through, trying to shove it through more, there'll be more resistance as well. I hope that makes sense, at least after I say it. Just think of it as ridiculous. You know, you have a mile-long cable versus a little paper clip. You know, it'll be easier to shove it through a paper clip than it will a mile's worth of conductor. So longer things have more resistance, and skinnier things have more resistance. The type of material can affect the resistance as well. For example, a copper wire versus styrofoam. Styrofoam we would call an insulator, which means charge isn't free to flow on it anyway, so its resistance would be really, 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 really high. Or infinite, you know, depending on what voltage source everything can become conductive if you push those charges hard enough, high enough voltage. But usually styrofoam doesn't conduct, and we'd say its resistance is infinite. So length, size, and the type that it's made out of. Ohm's Law, good, we just did that. So you can see the relationship there. The three ways, you can see the push. You want to figure out the push, you would need to know the current and the resistance. You can figure out the push. Resistance, you can think of that as a ratio of the voltage to the current. The push for what's getting pushed. The electric potential. Remember, voltage is electric potential. And current, you want to know how much is flowing? Well, we did that. You will never get shocked unless there's a difference in electric potential. You have a difference in voltage. Because charge will never flow. We discussed it, hanging from the power lines. Let's do that demo. It's not a power line, but how many of you know what the three prongs are in all your electrical cords? We use them every day. We plug things in. Positive and negative. And ground. Essentially, yes. Good. Usually the round one is ground. And what's that mean? That means it's literally connected through the circuit somewhere to a pipe stuck in the ground. Well, I've seen the pipe stuck in the ground here because the earth acts as a big sink for charge. You know, if this circuit's deficit of electrons and you connect it to ground, electrons will flow up and neutralize it. Or if you have an excess of electrons, they'll flow to ground and neutralize. That's what ground is for. That keeps the voltage, the electric potential, at zero. These two, it's essentially like the two sides of your battery, positive and negative. They call them hot and neutral. You can have a high voltage on one side and a different voltage on the other, a low. The low is not always zero, but you'd like it to be. And in most circuits, the neutral is the low and connected to ground. So they're both at 0 volts. So I separated the three cables here. I call this my suicide cord. I don't recommend you guys playing like this at home, but I have a GFCI rated power switch that's turned off and I'm not plugged in so that I don't hurt myself. That just means that if I accidentally touch it where I'm not supposed to and current starts flowing through me because there's a difference in voltage, this should trip and turn off the power. I haven't tested it yet. It's tripped, but not while I've been connected to it, so that's good. Pencil lead, graphite. It's a pretty good conductor. So I figured out black is hot and white is neutral. Black and white. Now, there's a standard in the United States, and most people follow it, but many times you cut open a cable and there'll be different colors. This is not always the case. I wouldn't just trust colors. But I've figured out which matches which. And so these two, if I put the pencil lead across the two, so that now there's, whoa, don't roll up, there's a path. The hot and the neutral are connected. If, like I said, it saw a difference in voltage. The hot was at 120 volts, and the neutral, which is connected to ground in this case, is at 0. Charge got pushed, and that's what would happen to your finger. All right, unplugged. Let's do the ground and hot. Balance these two. I meant for that to be off. Plug it in. Okay, now I can flip the switch. Ready? Never gets old. Now let's do the ground and the neutral. That one tripped the circuit. I know it's on. That's off. Plug it in. Ready? Well, that's what should happen. They're at the same voltage, same electric potential, both at 0 volts, so no charge gets pushed. So, in theory, I could plug this in and touch these two and be safe. And a lot of electricians know which one's safe to touch. Just for common sense, I'm not going to test that theory out, because you never know if they wired it right inside, but well, they had to have if we just tested all that, but why chance it? But if sometimes you got to check. I've seen many electricians work on circuits live. So if you're ever going to have to do that and you're not sure, test it first with something other than you. Let's say worst case, you got to touch it. Touch it with one hand only. Make sure you're not touching anything else, because if you touch it with both, it sees a path through you. Electricians are taught to only test things live with one hand. That way, at least maybe it would, if it's going to go through, it'll go this way and not through your heart. But anyway, you need a difference. So we have AC and DC circuits in this world. DC is batteries. That's kind of what we've been dealing with up until this point. It stands for direct current, which means when it feels a push, the charges, the electric field's established, and they all start moving in unison, they all move the same direction. The electric field doesn't change. It's always in the same direction, so the charges always flow one way. That's direct current. Batteries are like that. AC is alternating current, and it alternates means it changes direction. The charge flows this way, then it flows that way. The current goes one way, and then it goes the other way. The electric field must be alternating as well to make those charges do that. It oscillates. And we usually call that positive and negative, because if it's flowing one way, we'll call it positive. When it flows the other way, we'll say it's negative. How do you get it to flow the other way? Well, you change the electric field and you flip it. So say here's 0 volts. If we rise up to 120 volts, you can set up an electric field and they'll feel a push in one direction. If you want it to go the other way, drop this to negative 120 volts. And that'll set up the electric field oppositely and make the charges go the other way. Then make it positive, then make it negative, then make it positive, then make it negative. That's alternating current. I have a little LED up here. What color is it? Not sure? Yellowish, orangish, greenish, red. Why are you guys all different? Because, look, I hope the camera picks this up. This is cool. This is actually 2 LEDs, a red one and a green one. I can spin it around. This is because it's connected to alternating current. That's what comes out of our outlets in this nation, in most nations. It alternates. The electric field switches, and so the current switches. The red is when the current's flowing one direction, and the red LED lights up. When it flows the other way, the red LED can't light. They're like diodes, and diodes allow current to flow one way, but not the other. So the red's set up to flow one way, and the green's set up to flow the other way. And so when it's, say 120 volts positive, it flows through the red. When it's negative 120 volts and changing direction, it goes through the green. And it alternates, and you can actually see that. What do you notice between the red and the green? Yeah, space. That's where the power company's gypping you. We're paying for that. You guys don't seem too upset. Well, you shouldn't be. It isn't strobing. It's just alternating. So if this is 0 volts, then the power that's provided, you can think of this as the voltage and the current. It goes like this. It goes up positive, increases the electric field in one direction, but then it comes back down to 0 and then starts going the other way. And then this, and this, and this. This is AC current, AC power. If we were to put an oscilloscope up there and look at the signal, the voltage would constantly be changing because the electric field's switching. large this way, come back, large, it's like a pendulum. So the current would as well. It would change direction. It'd get pushed one way, then come back, get pushed the other way. But it has to pass through 0 to switch. That's where it was dark. Because for a brief moment, you aren't getting any power. But that's okay. That's how this works. We're not getting gypped. They know that. We know that. Yeah, Kate?
So when would you use a DC? Just
Yeah, we're going to get to that in the next chapter. It's induction, but I'll jump to the crux of it. We want power. We need to use energy. Batteries are a source of energy. This is a source of energy. The outlet is a source of energy. And we're going to use up that energy at certain rates. Do you remember that power is energy per time? Power is energy over time. It's the rate we use energy. Don't think of batteries and outlets as your voltage. They don't what do I want to say? They don't supply your charge. They're already there. They supply the electric field to start pushing them. And the energy, they provide that energy to do that. So they give energy to all those little charges as they flow through your circuit. And as they go through the LED or a light bulb, that energy gets converted to something else, heat or light. So you can use either to power almost everything, as long as you have enough. But there are certain things that only work, with AC power or DC power. And that's how, it depends on how they designed it. Generators and motors typically run on AC. Not all. You can make ones that run on DC. But if you make one that runs on DC, it won't run on AC and vice versa. And they have to account for this change or not. But the main reason we use alternating current in this country, and this is the next chapter, is because of transformers. It's the primary advantage of AC current. Transformers work with AC current so that we can step up or step down voltage. We can make high voltage or low voltage. And actually induce a voltage into another coil without them actually electrically being connected. It's very useful, and you're going to see how. And that's the primary advantage of AC and why it got chosen in this country, actually. Because it can be used in a transformer, which solved lots of other problems. So in reality, this actually gets up to, that's 120 volts coming out of the wall. It actually gets up to 170 volts. And negative 170 volts. But what's the average voltage? What is it? 110 would be what, up here? Close. Does that look like the average? On average, it's 0. Yeah, so they work out this thing. If we put a voltmeter up to the circuit and wanted to figure out, how much voltage are we getting? We don't want to see it keep changing all the time. Well, no. They give you a number that would correspond to the DC value. It's called the root mean squared. We're not going to get into it. But the value we'd use is 120 volts. So that everything else I've been teaching you in Ohm's Law, that's the number you can use, and it works out so that there's no discrepancies. Because if it's changing all the time, which value do you plug in? Oh, you plug in this root mean squared, which is kind of like an average that we can use that's useful for us. And that's how we can figure out all our circuitry and electronic problems. If we converted this to a DC circuit, we'd say it has 120 volts as well. But it would be constant. Always in the same direction. If it's AC, we still say it's 120 volts, but we know it's oscillating and changing direction. Okay, who wants to be a circuit? Help me out. We're going to charge up something and do some more circuits, but it's going to be a human circuit. Come on down. We're going to form a circle up here. Remember my capacitor? I'm going to charge it up while you guys are coming down. The more that come, the more fun it'll be. 2, 3, 4, 5, 6, 7, 8. Oh, we need more. Come on. Please. I've done this lots of times. I'm not going to kill you. I'm not going to burn you. Come on, come on. I need more. They won't like me. Now, if you have a heart condition, don't come down, but no sense chancing it. All right, form a circle around me and hold pinkies with your neighbor, please. Yeah. Thanks for being brave, people. All right, you remember, this is a capacitor. We got the two conductors separated by an insulator, the water on the inside, the aluminum foil on the outside. Charge is stored. Energy is stored. And it wants to get from this conductor to that conductor. The only way is if we give it a path. So if I were to touch the outside and the top at the same time, where would the current flow? Through me. Well, we're going to use the circuit. We need a switch. Who wants to be a switch? Okay, not yet. So I'm going to hold the foil. He's going to touch the bolt, and the only way he can get is through us. A circuit, remember you have to have a closed path. We discussed that. Or it won't be able to, the charges won't be able to see the opposite side. There won't be an electric field established. So you guys can't let go. All right, get off the table. We want to go through us, not the table. All right, when you're ready, touch away. Did you feel that? See, that was okay. Thanks. You didn't die. Couple things we can learn from this. Well, in addition. One, we discharge this, and now it doesn't have charge. I'll touch it. I'm not afraid. The charge is gone. Another thing I like noticing is you all kind of twitched at the same time. There's a section in the chapter, and I want to emphasize as well, electrons don't fly around the circuit at the speed of light. As soon as you close the switch and complete a closed path, the electric field's set up, and all the charges in your circuit feel that and start to move. So that's why everybody can feel it all at once. The actual individual electrons aren't going, whee! No. So the electric field can travel at the speed of light, nearly. But the charges themselves are moving actually really slowly. And because remember, they're moving already because they have a temperature. In the conductor, the free ones, the conduction electrons. So if they feel an electric field now in that direction, what are they going to do? They're going to kind of drift this way. They start, at one point they might be moving fast, but then their temperature is moving them back this way. And so they kind of, and probably about this fast. They just kind of drift along. They can bump into other charges, because if they shift this way and somebody else is in its way, sure, they run into it. That's our resistance. That's why a circuit has resistance. But they're not whizzing around. Yeah?
Does the size of the circuit make a difference in how much power it has? Like if we had twice as many people?
Yes. If you had double the size of your circuit matters. If we had twice as many people, we'd make it twice as long, and what do you think the resistance would do? By how much? Twice as much. So let's see. If we have a certain push capacitor, and we double the resistance, the current should be cut in half, and you wouldn't feel as much. Likewise, I've done it where instead of holding pinkies and making a skinny connection, I have you hold hands. That increases the cross-sectional area, doesn't it? It's like a thicker wire. What would you expect to happen? Bigger shock. Because if you hold hands, it's easier for the charge to get through. There's less resistance. And if the resistance decreases, the current can go up for the same push. That's why I had you hold pinkies, because you guys looked scared. In AC circuits, because the electric field keeps changing, it drifts this way, but then it drifts this way, and then it drifts this way, and then it drifts this way. So in an AC circuit, the charges hardly move at all. I mean, there's no net propagation along the individual charges because they keep shifting on you. Another thing is you guys all felt the same thing. A lot of people worry about being the switch. I don't want to touch it. Well, he felt the same thing as everybody else did. Again, because as soon as you close it, the electric field's established and all the charges start moving. And in a series circuit, that was series, where there's one path. In order to get through from me to the next person to the next person to the next. You have to get through them. That's why if there was a break, it would stop. There was no branching off. Oh, some current could go over here and some current could go over here. We had the same current going through each of us. The current is the same in a series circuit. You should note that. The current is always the same everywhere in a series circuit. I'll revisit it, but that's an important point. So how do we figure out this power? Because the electric company wants to charge us. No, it's too high. In general, this whole semester, power has been energy per time. How fast you use up that energy. Again, I don't expect you to replicate this minimal derivation, but I want to show you that that's all I'm getting to. In our section, our energy is electrical potential energy. It gets that from your voltage source. Remember, it takes work to separate charges. That's what your battery did and your power supply. Separates them, and now there's electric potential energy, and we're going to use it. Depends on how fast. Energy per time. All I'm going to do now is multiply both by charge. You see that keeps the ratio the same? Same charge on top, same charge on the bottom. However much charge is involved in your circuit. We'll just represent it with Q. And then rearrange those. Well, there we go. Who remembers what this one is? Current. Good. It's the flow rate of charge, right? It's how fast your charge is flowing. Who recognizes this one? Energy per charge. What's that? It's the voltage or electric potential. Same thing. Electric potential voltage is energy per charge. So, in circuits, we can find the power. It's current times voltage. So it looks like something different. A new formula, a new equation, a new guide to thinking. But remember, all it's telling us is it's how fast you're using up energy. It's the energy per time. Because this is the flow rate of charge. This is how much energy each charge has. So it's the energy per time. And that is in a watt. Current is in amps. Voltage is in volts. And power is still in watts. See, you look on your light bulb and this one says, oh, it's 100 watts. I know what that means now. That means I can think of that as, oh, I'm using 100 joules per second. That's what a watt is, joules per second. Why do I keep putting my chalk down where I don't want it? And a watt, remember, is a joule per second. So 100 watts, I'm using 100 joules per second. Or I know now that that's the current times the voltage. So, will you help me? Because have you guys seen these? They're great. You can buy them. They're called kilowatt meters. And they tell you how much anything is using. It'll tell you the current flowing, the voltage, the wattage, or how much money, kilowatt hours, which is in terms of energy. So if I turn it on, we let it come, how many volts?
Looks like 121.
121 volts, and the current?
0. That might be it.
There we go.
Now 0.75.
0.75 amps. The watts?
92.
And so it's actually only using 92 watts. It's listed as a 100 watt bulb, but we're only using 92 watts of energy. It can tell you the frequency and the kilowatt hours, but we won't go there. Let me change it out. Because we're green here, right? This is a 100 watt equivalent. It's but how much watts does it really use? Basically, 100 watt equivalent means they made it so that it's about the same brightness as this 100 watt incandescent bulb. So they should be about the same brightness. But let's see how much energy it uses. Turn it on. How many volts?
So 121.
Same voltage, same power source. Current. Oh, come on. Wake up.
Now 0.22.
0.2 amps. The last one was 0.75. So it's drawing less charge flow, current. That's good. That should tell me it's using less energy. Let's see. The wattage is?
13.
Thank you. 13 watts to have the same brightness. So yeah, these do in fact really use a lot less power, energy per time. So do you want to spend your money on 100 watts or 13 watts? Well, that's up to you. They both have advantages, but they do last longer and they do cost less. That much is true. Since we have that term all the time, I'm going to rearrange this. Energy is power times time. So power was watts and seconds. If they do this by a factor of 1,000, they call it kilowatts. But it's still a unit of power. And they usually don't use seconds, the power company. They use hours. A kilowatt times an hour. Kilowatt hours. So when you hear that term, that's actually energy. That's how much energy is being used. So then that's how they charge you. 15 cents per kilowatt hour. So you can measure your current and your voltage in your circuit, know how much power that appliance uses. And if you run it for an hour, you can figure out how much energy the power company is going to charge you if you want. Or you can buy a kilowatt meter and let it tell you. Now we can do a series and parallel circuit. Let's do these two demos first, because they have more to do with resistance. I turned on the power, 6 volts across this light bulb. Is charge flowing? I didn't hear too many confident people. Charge is flowing, but you don't see the light. Can you explain? Charge is flowing, but I don't see the light lit up. Yeah, there's too much resistance. This is in series with the light bulb, so you can see the power supply. Like us in the circle. This is one stage, then it has to go through here, and then it has to get back. And this is just a coil of wire. But there must be too much resistance in our circuit for this push, this voltage push. Charge is flowing because it's closed, a complete path, but this needs more power to run. It needs more energy per charge to go across it. Liquid nitrogen again. It's really cold. Most conductors, when they get cold, decrease their resistance. So not only can the size and the material matter, but its temperature affects resistance as well. Is it lit yet? So that tells me the fact that it's lit, more current must be flowing in the circuit. And if more current's flowing, the resistance had to have decreased. This got colder, so I make the connection that, when that gets colder, its resistance drops. And if the resistance drops, we can push more charge through. And as it warms back up, the reverse happens. Is it out yet? But I assume you saw it dim. Oh yeah, it's out. And now I'll turn the power supply off. Incandescent, yes, Kate?
Okay, I thought it was the resistor that created the heat and the light.
You thought the resistor is what created the heat and the light. It can. Yeah, if you send enough charge through there, the resistance, think of it as friction as those charges try to move around and wiggle in there. Yeah, it heats up, and a lot A lot of the energy, electrical energy of a circuit is dissipated in heat. That's how this lights up. It heats up the wire in the light bulb, and as its temperature increases, it increases the energy of the wavelengths that it emits, it radiates. And this got into the visible range so we could see it. That's how incandescent light bulbs work. This has a filament inside, and it's really skinny, so it has a lot of resistance. And so when you send the charge through, a lot of that electrical energy is converted to light, heat transfer. And I can show that with this. You see this wire? I'm going to put 120 volts right across this little wire. This should be a lot of resistance. So, sorry. This is actually relatively little resistance because that's all there is. It's the only thing it has to jump across. And so it's going to push a lot of charge through there. Big push, little resistance, a lot of current. Watch what happens. Plug it in. Flip the switch. Ready? Current's flowing. It heats up and glows. Oh, too much. And so if you can sustain that glow by making it a little longer so it doesn't break, or putting it in a vacuum so it doesn't react with air or oxygen or some noble gas, that's what they do in a light bulb, incandescent light bulb, so that it stays glowing. Eventually it burns out and you got to get a new light bulb. And this is how fuses work. If you put this in series with your appliances, the same current flows through this as flows through your appliances in series. And if this burns at 10 amps, let's say if 10 amps or more flow through this and it breaks, it can't handle that, then do you get power to your appliances? No. So if your appliance will fry with more than 10 amps, you want to keep the current under 10 amps. You put in a fuse rated at 10 amps. A lot of people think, oh, my fuse blew. It's a 10 amp fuse, it blew. Oh, I don't have a 10 amp fuse. I have a 15. So they put the 15. 15's bigger, that's good, right? So they put it in. Well, what does that mean? Now it won't blow until 15 amps flow through the circuit, which could fry your appliance. Bad idea. So always abide your amp, your fuse. Yes, Kate?
On the line here, the resistance was so great, it couldn't even...
Yeah, the resistance of the circuit was so great when this is warm that this couldn't push enough charge through this to make it light. Charge was going through it, but not enough to heat it up and make light. So I chilled this, decreased the resistance here, which decreased the total resistance. And so for the same push, we can now get more charge through.
Okay, but what would happen if you didn't have the resistor at all?
At all? Then if I just removed this and shorted across it, so there was still a complete path, I removed the resistance from the circuit, and now it's just this resistance. There'd be less resistance total, and probably enough charge would flow and it would light.
It wouldn't blow up.
It might. Yes. I'm not going to try it for that reason. Because I'd measure this resistance first.
So it's the resistor that maintains it at a level that we get constant.
That we can use, yeah. Remember your question before, Ennis? We can use this to regulate how much current flows through. If we know the resistance of this, we know its power, we know how much voltage and how much current it needs, and we can hook it up directly. We can control that and make it perfect. This one wasn't, so yeah, we put this in series with it to regulate it. Good questions. So again, resistance can be affected by size, shape, length, skinniness, what it's made out of, and the temperature. All can affect. If we were sweaty and we did that circuit up here, water's a better conductor. So the total resistance in the series circuit would drop, more current would flow, and it hurt us more. Yeah.
I think it's kind of counterintuitive to me that chilling the metal would increase its resistance. Wouldn't
It decreases.
I'm sorry, it decreases. Wouldn't the slower molecules in the water make it less likely for the charge to move?
I hear you. It can seem counterintuitive. I like to think of it this way. They're all kind of crammed in there trying to move. And when you chill them, you guys now know that they're moving a little slower. They're more rigid. They're closer together. And it's kind of like, if I won't do it, but say we all lined up here shoulder to shoulder. You know, and we were all touching shoulders, kind of rigid, like we're cold. And I pushed over here. It would probably propagate through us and the last person would get tipped over or lose their balance. But now line them up and there's a little space between because they're wiggling around faster and not touching each other most of the time. If there's a little space between each person, I can push the first person, he'll probably move. He might hit the second person, but eventually it doesn't seem to get through as well. Think of that. The hotter something is, the more farther apart they are, it's not as rigid and it provides more resistance for the charge. So, I think it's more important to write this than it is to do that. So, series versus parallel. 1R. 3 resistors in series. The symbol for battery looks like this. So these are resistors. You can think of them as light bulbs or different appliances or whatever. And here's a battery or voltage source. That would be in series. See how there's one path? In parallel, they can split. The current can split. So this has one pathway from one side to the other of the battery, or this has options. When the current comes out to this point, oh, I can go up, or I can go this way. So the current can split over here. So in series, if you disconnect one of these light bulbs or it burns out, what happens to the other two? They go out. How about if this one burns out? Yeah, only that one goes out because the others can still see the electric field, both sides of the battery. Very important. So in this one, the total current, and by that I mean what comes out of your voltage source, your battery, your power supply. What's coming out right here? Well, it's going to be the same current that flows through resistor 1 and 2 and 3 because it's one circuit. It has to be the same. In parallel, it does not. The total coming out, there, is going to be the sum of what goes through your individual ones. Whatever current goes, I'll just turn around. Whatever current goes through resistor 1, remember the current could split. If it comes out here, some of it goes this way, some of it goes that way, and some of it goes that way. And so if you were to measure the current through each resistor and add them together, your power supply has to provide that initially. So the more resistors you put in parallel, what if we added more? What would happen to the current? It would increase. If you had more things to split up among, you're going to need more to start with. So there's more current in a parallel circuit. Hooking things up in parallel means you draw more current out of your power supply. In series, what happens if you add more resistors? Let me do it in steps. If you add more resistors, what happens to the total resistance of this circuit? Oh, we got all three. Go up, go down, stays the same. Let's say our circuit's like this, and then we add some more on that it has to go through. It's like making it longer. It has more things it's got to get through before it can get back to the battery. Does that increase or decrease the resistance? Increase. So adding more resistors in series means the voltage source sees more resistance total. It's got to get through more stuff before it can get back. And so if the resistance increases, Ohm's law tells us the current drops. So adding things in more resistors in series allows less current to flow. Adding more resistors in parallel means there's more paths. They need current, and they each need it. So you got to provide more current in the first place. The total resistance the voltage source here sees would drop. Say that again. More resistors in series, it's got more to go through. Total resistance goes up, current goes down. Add more in parallel, hey, it's like making it wider. There's more paths to get across. So the total resistance drops. When you hook things up in parallel, the total resistance drops, decreases. And if the resistance goes down, the current goes up. And you draw more from your power supply. Does that make sense? We did it. I'll show you that happening next time, but I want you to get the theory. Thanks.